You know, fire is one of those things we see all the time, right? A candle flicker, the flame on your stove. It seems so simple. But behind that familiar warm glow is a really fascinating chemical story. So today, we're going to peel back the curtain and really dig into the science of combustion to understand what's actually going on.
All right, first things first, let me ask you something to get the wheels turning. Just picture a birthday candle flame right next to a glowing piece of charcoal from a barbecue. I mean, they're both hot, they're both technically burning, but they look totally different. So why does one have that dancing, flickering flame while the other one just glows? And that right there, that's the mystery we're going to solve today.
Yeah, just look at the difference. On one hand, you've got the candle with its very obvious, visible flame. And on the other, you have charcoal, which just radiates this intense, red-hot heat without anything you'd really call a flame. This visual difference is actually our first big clue. It tells us that even though both are burning, something really different is going on at the chemical level. And here's the thing. They're both actually examples of the very same fundamental process, combustion. Simply put, combustion is just a chemical reaction where some kind of fuel mixes with oxygen and releases a bunch of heat. That energy that gets released is what we see as light, either as that familiar dancing flame or as a steady, intense glow.
Okay, so here's what we've got on tap for this explainer. We're going to start with the basic recipe for fire, then we'll take a peek inside a single flame. After that, we'll look at how we measure the power of different fuels, and finally, we'll touch on the environmental price we pay for all this burning.
All right, let's dive right into our first big topic, the recipe for fire. What are the absolute must-have ingredients for something to catch fire?
You know, it all boils down to what's famously called the fire triangle. You always need these three things. First, you need fuel. That's just something that can burn. Second, you need air, or more specifically, the oxygen that's in the air. And third, you need heat. But not just any heat. You need enough of it to hit a very specific, critical point.
And that special point, that critical temperature, it has a name, the ignition temperature. This is the magic number. It's the absolute lowest temperature a substance has to reach before it will burst into flame and start burning on its own. Every single fuel, from paper to wood to gasoline, each one has its own specific ignition temperature.
Okay, so now that we know about ignition temperature, let's play with the idea a little. Here's a wild question for you. Do you think you could boil water in a paper cup over an open flame without the cup itself catching on fire? I mean, come on, it's paper. It should just go up in flames, shouldn't it?
Well, believe it or not, it's totally real. In this experiment, you can see a regular paper cup full of water being held directly over a flame. And yet, the water inside is heating up, but look closely. The paper itself, not burning. So what on earth is going on? And here is the super cool science that makes it all work. As the flame blasts the bottom of the cup with heat, that energy is immediately sucked up and transferred into the water. See, water is an absolute sponge for heat, and it pulls that energy away from the paper so fast that the paper itself never ever gets hot enough to hit its ignition temperature. It's a perfect, real-world example of the principle.
Okay, so we've got the recipe for starting a fire down. But what about the flame itself? Let's move on and actually take a look inside a single flame for a quick anatomy lesson.
And this takes us all the way back to that first question we asked about the candle and the charcoal. Here's the answer. A flame only shows up when the fuel turns into a gas, when it vaporizes as it burns. With a candle, the wax melts, gets sucked up the wick, and then turns into a vapor. It's that hot vapor that we see burning as a flame. Charcoal, on the other hand, doesn't really turn into a gas. It just burns as a solid. And that is the fundamental difference.
But what's really fascinating is that a flame isn't just, one blob of fire. It's actually a superstructured thing with different zones, and each zone has its own unique properties. Let's break it down.
Let's break it down into three basic layers. First, you've got the outermost zone. It's often this faint blue color. This is where there's plenty of oxygen, so you get this really efficient, complete burn, and guess what? It's the hottest part of the flame. Then you have that bright yellow middle zone. That's where most of the light we see comes from. There isn't quite enough oxygen here, so the burning is incomplete. And finally, that dark innermost zone right around the wick is actually the coolest part. It's mostly just hot wax vapor that hasn't even started to burn yet.
So we've dissected a single flame. Now let's zoom out a bit and talk about the fuels that make them. How do we even compare them? How do we measure their firepower?
Well, the way scientists measure this is with something called calorific value. And it's a pretty simple idea. It's basically, how much bang for your buck do you get? How much heat energy can you squeeze out of 1 kilogram of a fuel when you burn it completely?
The higher that calorific value, the more energy is packed inside. And wow, when you start comparing fuels, the difference is just staggering. You start with something like a cow dung cake, a traditional fuel that gives you maybe 6,000 to 8,000 kilojoules. Then wood is a pretty big jump, up to around 20,000. But then, look at the modern fuels. Petrol hits 45,000, LPG is even higher at 55,000, and then there's hydrogen gas, which is just off the charts at a whopping 150,000.
This chart really puts it all into perspective, doesn't it? The energy you get from that cow dung cake is just a sliver compared to what's in petrol. And then hydrogen, it's in a completely different league. This massive difference in energy density is exactly why the choice of fuel is so critical, whether you're just cooking dinner or you're trying to launch a rocket into space.
But of course, all that incredible energy, it doesn't come for free. For our last section, we have to look at the flip side of this whole process, the unseen environmental cost of all this combustion.
You see, the big issue is that when we burn fuels that are based on carbon, and that's most of them, like wood, coal, and oil, the reaction is never perfectly clean. It releases a whole bunch of nasty stuff. You get these tiny particles of soot that cause breathing problems. You get carbon monoxide, which is a poisonous gas. And then you have the two heavy hitters, carbon dioxide and the oxides of sulfur and nitrogen.
And that carbon dioxide, well, that's the big one. Pumping more and more of it into the atmosphere acts like a blanket, trapping heat and causing the planet's temperature to rise. That's the primary cause of global warming, which leads to scary consequences like melting glaciers and rising sea levels.
And it's not just CO2. When you burn things like coal and diesel, they release sulfur and nitrogen oxides into the air. These gases mix with the water up in the clouds, and, well, they form acids. So when it rains, it comes down as acid rain, which is incredibly damaging to forests, crops, buildings, and really entire ecosystems.
Now, it's not all doom and gloom. The good news is we know about these issues, and there's a big push toward cleaner alternatives. Take compressed natural gas, or CNG, for example. It burns way more cleanly than gasoline or diesel, producing much smaller amounts of these harmful pollutants. It's a really important step in the right direction.
So that kind of brings us to the big final question, doesn't it? Look, combustion powers pretty much everything in our modern world. It has given us unbelievable progress, but it's clearly come with a very steep environmental price tag. So the real challenge for all of us moving forward is to figure out how do we keep that power but manage the cost in a way that's smart and sustainable for the planet.